Hello dear students, welcome you all. In this lecture, we are going to discuss about the change in entropy during a reversible and irreversible process, right? We will start from a reversible process, right? Change in entropy during a reversible process, right? Uh, then we will come to the case of irreversible process, right? We know very well, we have found an expression for change in entropy, that is ds is equal to integral of initial state to final state, delta q upon t, right? This is the expression. I am going to give this equation as name equation number 1, right? So now let's consider a reversible process. So for that, let's consider the reversible Carnot cycle. That is a good example of a reversible process. You know very well, in reality, in nature, all the thermodynamic processes that take place are irreversible. You can say that ideally speaking, there is no reversible process in the nature. But for the sake of simplicity, or for various calculations in thermodynamics or understandings, we take the case of reversible processes. Even we can create situations where experiment is performed under controlled environment. So we can say this process is quasi-reversible, right? It is not fully reversible, but we can say it is very close to the reversible. But in reality, no process in the nature that takes place it is irreversible, right? So I am considering the case of reversible Carnot cycle, right? So you know very well, in case of reversible Carnot cycle, you have the diagram. This is PV diagram, pressure, and this is pressure, and this is volume. Clear? So when we draw the reversible Carnot cycle, we know it is of this type. Right? This is right. This is Carnot cycle, complete cycle. These are the different points A, B, C, D. In this cycle, these AV and CD are two isotherms, means they are taking place at a constant T1, T1, right? Similarly, it is T2 and it is a T2. Means when the given gas expand from here to here, it expands isothermally. The temperature is a constant. Clear? So when the gas goes from here to here, then we have change in temperature, right? It changes from T1 to T2. So again, when we come back from here to here, again there is temperature is same. So here it is a point D. The temperature is a T2. Then once again we go back to this side, and we have reached at point A. So it makes the cycle complete, right? So I can write here, these are two isotherms, this and this one. These are isotherms and these are adiabatics, right? The same is here, right? Isotherms means, once again I am saying that temperature is same when the gas is going from the system is going from this position to this. Clear? And when system goes from this to this, the process is adiabatic. Clear? There is no exchange of heat between the system and surrounding, but all P, V and T changes. Again, same thing here, right? In this case also, it is adiabatic, so there is no exchange of heat between the system and surrounding. So again, the PVT all changes. You can see here, P changes, V changes and T also changes. But as we grow from here to here, right, and here to here, then you can see the temperature is same. So this is basically what? This is the expansion, as I told you. So as I told you that this is expansion of the gas when heat is added, expansion, and we have added heat, Q1 to the system. And this is what? This is contraction. Clear? Compression or contraction, you can say. Compression. Clear? So during compression, heat, Q2 is rejected from the system. Right? This Q1 is added. Right. Now, we want to calculate the change in entropy during all these four paths. So, if you look at the adiabats, right, this and this, we know during the adiabatic process, clear, there is no exchange of heat between the system and surrounding. Clear? It means this factor is equal to 0. So it means for both these, this one and this one, ds is equal to 0. Clear? Change in entropy is equal to 0. Now come to the this change A to V. When the system go from A to V, clear, it is basically expansion. When we added heat Q1, then the change in entropy is equal to Q1 upon T1. Obviously, so when we go from here to here, C to D, it is what? Compression. Clear? Contraction or compression. Then C to D. Then you will get what? You will get minus Q2 upon T2. I took negative sign in the heat because heat is rejected from the system. Heat added to the system is taken as positive. Taken away from the system is taken as a negative. Right. So now you can see that the total change in entropy that will be equal to, that was delta Q upon T, that will be equal to Q1 upon T1 minus Q2 upon T2. It is the sum of these two, right? But we know for a Carnot cycle, there you have learned it in your 12th class also, Q1 upon T1 is equal to Q2 upon T2. Clear? We have learned it in thermodynamics when we studied about the Carnot theorem and Carnot cycle. So Q1 upon T1 is equal to Q2 upon T2 means this is equal to 0, right? So it means ds, change in entropy during the entire this reversible process, when the system goes from here to here, then here to here, here to here and here to here. Clear? So during all this process, clear, there is no change in the entropy, ds is equal to 0. So we can conclude that during a reversible process, complete reversible process, 100% reversible process, there is no change in the entropy of the system, right? So this is the first result. Now we are coming to the second result, that is irreversible process case. So for irreversible process, let's write here, change in entropy during irreversible process. Clear? So let's take a case of irreversible process when we have two bodies. This is body A and this is body V. It is at temperature T1, it is at temperature T2, clear, such that T1 is greater than T2, right? So when these bodies came in contact with each other, obviously the heat will flow from first body to the second body, right? Because it is at high temperature. So let Q is the amount of heat that flow from body A to body B, clear? So loss of entropy or we can say decrease in the entropy of entropy by body A. It will be how much? Q upon T1, negative, because heat is rejected from the system. Similarly, gain of entropy, clear, by B. Why I am saying the gain of entropy? Because here we will get positive sign Q upon T2. The same amount of heat that is rejected by system A is added to the system B, right? So obviously the heat is added to system B, it means its entropy is positive and it is gain in entropy, right? So total change in entropy, you can say ds is equal to Q upon T2 minus Q upon T1. I added these two factors, then I will get here T1, T2, T1 minus T2 bracket or Q, clear? So you can see here that this is the expression for a change in entropy. ds is equal to this. Now it is very clear that the heat is fixed. T1 and T2, we know T1 is greater than T2. It means this factor is positive. It means ds is positive. It is not equal to 0, right? You can see here. So this is very important result of the thermodynamics, that in a irreversible process the entropy of the system will always increase. Clear? You can see here entropy will always be positive, as all the process in the nature, as I told you in the beginning, they are irreversible. It means in the nature the total entropy is always increasing. This is also called as the law of increase of entropy. We are going towards the increase in disorder in the system. I mean, heat is transferring from hotter bodies to the colder body. You can see in the real life examples also, but it is not possible that heat flows spontaneously from the colder bodies to the hotter bodies. In fact, that will reduce the entropy, but this is not possible. So from this all discussion, we got the conclusion that during a reversible process, entropy change is equal to 0, whereas during a irreversible process, change in entropy is positive. Clear? So this is all about the change in entropy during a reversible process and irreversible process, right? So thank you very much.